molecules can have the same formula and bonds, but behave completely differently. Why? Because of stereochemistry. For example, glucose and galactose share the same formula, but their different 3D arrangements give them distinct properties. Let's start with R and S configurations used for chiral centers. A chiral center is a carbon atom bonded to 4 different groups. Take lactic acid as an example. The central carbon is bonded to OH, carbon trihydride, and COOH, making it chiral. To assign R or S, we follow a few steps. We will follow CIP rules. Step 1. The atom with the higher atomic number gets higher priority. For lactic acid, O has highest priority, then COOH, then carbon trihydride, and hydrogen is lowest. Step 2. Orient the molecule so that the lowest priority group points away from you. We position hydrogen at the back to apply the rule correctly. Step 3. Trace the path from highest to lowest priority among the 3 visible groups. If the path is clockwise, it is R. If it is counterclockwise, it is S. This system helps us distinguish between enantiomers, which are non-superimposable mirror images of each other. Here's R lactic acid and its mirror image S lactic acid. They look alike, but behave differently in biology. Now, let's look at E and Z isomerism in double bonds. Consider but-2-ene, a simple alkene, which can exist in 2 different forms. In alkenes, rotation around a double bond is restricted, so the relative positions of groups matter. Here also, we use the same priority rules. If the higher priority groups on each carbon are on the same side, the isomer is Z. If they are on opposite sides, the isomer is E. In cis but-2-ene, Z, the carbon trihydride groups are on the same side. In trans but-2-ene, E, they are on opposite sides. Think of Z as zusammen, in German, meaning together, and E as entgegen, meaning opposite. Stereochemistry is not just theory, it changes reality. Enantiomers of the same molecule can smell different, or one may be a life-saving drug while the other is harmful. Enantiomers can even taste different. One form of aspartame is sweet, while the other is bitter. E and Z isomers can have different boiling points, solubility, and reactivity. For instance, cis but-2-ene boils at about 3.7 degrees Celsius, while trans but-2-ene boils lower, around 0.9 degrees Celsius. So, stereochemistry gives molecules their unique identity, even when everything else looks the same. In the next video, we will explore how stereochemistry affects reaction mechanisms like SN1 and SN2.